بسم الله الرحمن الرحيم. الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to the 8th class. Today, inshallah, we're going to be continuing on the topic number 2, kinematic modeling. Let's start with the recap of we discussed. Before the recap. So today's lecture, I consider it personally to be very important in the sense that it's pivotal in what comes. If you missed the stuff that, not missed, but at least if you had struggles with understanding the basic concepts of what was before, today you can catch up in the sense that if you just enter today and take what was mentioned in this lecture as the starting point, you can move on in the rest. The only thing is that everything will be for you matrix multiplication. So if you're good with that, you can continue with the course. The previous part is what gives these matrix multiplications meaning. Okay, so if you're comfortable with doing matrix multiplication, moving from now on should be okay. The previous part, or the first part, is giving these matrix multiplication the abstract meaning in general, and this is the analogy going from 2D to 3D, going from rotations to translations and so on. And that's why we're going to be going back and forth to this abstract view and the matrix multiplication so that you never forget what these objects actually represent. And most importantly, when we come to the more advanced stuff, we're going to find weird formulas, weird expressions that we are using, very efficient. They do what we want. If you don't have this abstract understanding, they don't make sense to you, because in terms of matrices, again, now you understand the drill. Let's start by a recap of the notations we're using in the kinematic modeling. Kinematics means there's no forces, no torques, just frames moving around. Each frame we denote either by psi sub I or by curly brackets I. So we have a number of frames here. As you can see, one attached to the base of the mobile robot, one attached to its end effector. There's an object in the middle we're interested in. We have a stationary frame. We have some motion capture system or camera frame that we observe the other systems with. The relative pose of some frame I with respect to some frame K is given by homogeneous transformation matrix. This homogeneous transformation matrix is an element of the special Euclidean group in 3 dimensions. It's given by a pair. There's no other information in this 4x4 matrix in 3 dimensions other than some rotation matrix, which denotes the relative orientation between these two frames and the displacement of the origin of frame I expressed in frame K. So we have these two pieces of information. We put them in this matrix form such that the group operation, everything we're going to be doing is matrix multiplication. Then we discussed, this has a group operation. So if we take two homogeneous matrices, we get another homogeneous matrix. The intuition behind that is that if you have some homogeneous matrix of frame I with respect to frame J, and you have another transformation between frame J and frame K, then the group operation, which is in this case matrix multiplication of two 4x4 matrices, will give us the relative pose between frame I and frame K. Okay? And these frames can represent anything. They can represent a robot body, a robot end effector, a robot's joint. They can represent a camera frame, a sensor frame, whatever. Okay? So this is in general. And the h of J with respect to K, or any two frames in general, is the same as the inverse of this matrix of K with respect to J. And this inverse is not any, again, what's inside is not any 4x4 matrix. It has some special structure, which gives us these two components of it. And the same for rotation matrices. If I have the rotation matrix of K with respect to J, and I want to look at J with respect to K, then it's given by the transpose of that. So the transpose is of rotation matrix flips the indices. The inverse of homogeneous transformations flips the indices. Okay, so because rotation matrices, they have this property that the inverse is the transpose. Homogeneous transformation matrices doesn't have this property. Okay. Yes.
Can you write Hij times HJK? Or
This time, what do you mean by the times here? Matrix multiplication? Matrix multiplication, yeah, okay. So?
Okay, can we swap it?
Swap it, okay, that's a good question. Can we swap this information? Why? It's not an abelian group, exactly. It's not an abelian group, so commutativity doesn't hold. You get something completely else. You get another homogeneous matrix. Does it have any meaning? No, it's rubbish. Okay? You just get some homogeneous matrix, but this is the order that we follow. with indices, whenever we're talking about a point or a frame or a homogeneous transformation expressed with respect to something, then we should always have this canceling of indices. Okay, so J up, J down, then these two cancel each other, and then you have some, this is correct. Okay, if you do it the other way around, okay, then the J would be on that side and here, and it does not match with these. So these two, they don't cancel, these two cancel out. This is just the notation that we use here, and of course it has this physical meaning behind, okay? These homogeneous transformations, they are not matrices. It's not just matrix manipulation. These correspond to isometries on Rn. So if you did the homework, then you see all of these homogeneous transformations is actually one frame moving, okay, or represented as a an isometry on Rn, from Rn to Rn. And we're going to come back to this point later, inshallah. This is something we didn't discuss, but should be trivial to you. And I just put it here for analogy with what is to come. If I'm talking only about a point mass, okay, so the only configuration, or the point mass translating in space in 3D, then this point mass doesn't have any orientation. You're familiar with this concept, okay? So point mass doesn't have any orientation. Then the only way the only numbers, or the only variable I need to describe this point mass or this configuration of it is three numbers that correspond to this location of this point in this frame, which is the stationary frame. Okay, so this is the psi b with respect to s. It's 3 vector. Again, vector as in 3 numbers. Okay, its configuration space has some Euclidean structure. It has some Rn structure, so you're familiar with it. Rate of change of configuration is the rate of change of this variable, and the velocity expressed of this point mass expressed in the S frame is something that you usually think of it as exactly the same as the psi dot. So the rate of change of position is velocity. So it makes sense, right? I'm not saying anything new. This is only in R3. This is only in Rn. Okay, so this fact that the rate of change of position is equal to immediately to the velocity without any transformations in between this is like a consequence of the Rn structure, of the Euclidean structure that Rn or R3 in general has. When we go to the rotations, things become nasty because we don't have this Euclidean structure. We don't have this vector space structure. The configuration, as we mentioned, is given. Now we're discussing only rotation part. Okay? So we have one frame. Now we need to talk about frames. So now we have the orientation of one frame with respect to the other. The frame that's moving, and it's fixed to some body that's rotating, we call it frame B. And then we have one that's fixed, is frame S. And this frame B is rotating around some axis. This axis here, we just denoted in red. So you all visualize it, right? So for example, if I say that this axis is aligned with the ZS axis, then this body would be doing something like this, right? It's clear? If it's aligned with the XB axis, then it's doing something like this. If it's aligned with the YB axis, then I don't know which one. I think it's this one, right? The other one I didn't do, okay? So one is in XB, one is rotation around XB, one is rotation around YB, one is rotation on Z. But in general, I can be rotating around this frame, for example, and I can do something like this, right? So this axis I'm rotating around is something abstract. So that's why I put it here in red. You understand it even without numbers. It's something abstract as a free vector. The rate of change of the configuration is what we call the R dot. And where does it live? It lives in the tangent space with respect to the manifold SO3 or the Lie group SO3 at some point, which is the same point that this vector lives at. Okay. Now we can talk about angular velocity. The angular velocity is not the same as the rate of change of configuration. So the angular velocity is not the rate of change of the configuration. The angular velocity is what we call an element of the tangent space of SO3 at the identity. The Lie group has an identity. It's a very special point that doesn't change any orientation. So we know where it is. We know what it means. And we call this small SO3. And this was the Lie algebra SO3 of the Lie group capital SO3. And then we had some, and here I represented, this is in frame star. So you can have this angular velocity of frame B with respect to frame S expressed in any frame. And the first two frames that come in your mind are what? frame B, and frame S. Okay, so I can represent this in frame B and frame S. So if I represent it in frame B, then I get this kinematic relation between the rate of change of the configuration and the angular velocity. Or if I represent it in the frame S, I get this representation. Of course, you see, okay, this is matrix multiplication. It makes sense. This is a 3 by 3 matrix. This is a 3 by 3 matrix. This is another 3 by 3 matrix, but it has a very special form. It was skew symmetric. How did we know that it should be skew symmetric? If you remember from last time, when we derived that the tangent space should satisfy that R dot multiplied by R transpose is equal to minus of R dot R transpose all transpose. Okay, so if you go back to the lecture, you find that elements in the tangent space should satisfy this property. And if we look at the tangent space at the identity, we know that it should be skew symmetric matrices. Just that this is differentiating the condition that we had on SO3. But these two angular velocities, they have a very special meaning because this is the angular velocity. We think about it this way. This is the angular velocity of body B or of frame B that's it's attached to some rotating body with respect to the frame S. In this example, this is the stationary frame expressed in frame B. This one is the angular velocity of frame B with respect to frame S expressed in frame S. These matrix multiplication in this way, okay, you're comfortable with, but again, don't forget that this comes from the Lie group structure of SO3. So this movement or this curve or this rotation is a function of time. We consider it as a curve on SO3, and this R dot is a tangent to in the tangent space to this at this point R. And then we have this special space, which is the Lie algebra, and we translate this vector to this space. Okay, so we map this R dot to that space, and this mapping only because how SO3 is just a matrix multiplication. That's it. So, but you see, so we're at this expression, it's matrix multiplication in the algebra multiplied by some transformation, which is another matrix multiplication, and gives us another tangent vector in another space. So, and this is what I meant by everything is matrix multiplication in the end, but there's a lot of geometry behind it. Okay? Any questions so far? Right.
Or as we know later, it could be angular acceleration.
Angular acceleration, we haven't talked about angular acceleration at all. If you want to think about it, it's maybe the omega dot, right? Because if this is angular velocity, then the rate of change of it is this guy. And this is completely different from R double dot, right?
R dot here represent only the change or
the rate of change, exactly. R double dot is something completely wild. I'm not going to discuss about it, okay? But again, in terms of this way, you can see that R double dot will be the time derivative of this multiplied by that plus time derivative of this multiplied by that. So it has two terms. We're going to go into area I don't want to. Okay. Another question here? Yeah, which one? Applies only to? You mean in 3 dimensions? So if we had SO2, this wouldn't be the case? Is that what your question? If we have SO2, we have exactly the same form. And we're going to have some example to see what happens when we go to 2 dimensions, because this expression boils down to something very trivial and you're all familiar with it, but we're going to be showing it in details. So. Yes. We don't need it to pass by the identity. It can live out of the identity. And then we map to the identity by getting this quantity. So this is what this expression tells. So even if you don't have it at the identity, think of it this way. Multiply R by some angular velocity, you get this guy. Multiply R inverse, which is the R transpose, by that guy, you get the angular velocity. And this is actually how we defined it last time. If you remember, we defined the omega hat as the R transpose multiplied by R dot. One is a pre-multiplication, one is a post-multiplication, which is just rewriting these expressions. No, doesn't need. As a vector space. As small one or big one? Big one, yeah, it's a manifold, yeah. That's right.
When we're talking about the dimension of this tangent space,
yeah,
set,
It is equal to 3. Yeah, it is equal to 3. The dimension of capital SO3 is 3. The dimension of the tangent space at every point is also 3. And the dimension of the tangent space at the algebra, at the identity, which is the same, is just one particular special one, is also 3. And this is why this SO3, even though it's a 3 by 3 matrix, it only has 3 dimensions in it. It's like 3 only numbers. And if you remember last time, we introduced this tilde map or this S map that would take any 3 vector and put them into a skew-symmetric matrix that was like x1 minus x1, x2 minus x2, x3 minus x3, the rest are 0 on the diagonal. So this was this information. So, and this says, and it has an inverse, which means it's bijective. So if I have any 3 vector, you can write it in a skew-symmetric form. If I give you any skew-symmetric matrix, you can write it in a 3 vector. So that's why it's 3 dimensions. Okay. Other questions? Okay, good. The natural question is, when we go to rigid body motion, which is translation and rotation at the same time, is it easy or is it complicated? Now let's see. Configuration is a homogeneous transformation matrix from body B to body S. You all know what that means? Okay, clear? It's another manifold, another Lie group. We call it SE3. The rate of change of the configuration is a vector at the tangent space to SE3 at that point HB of S. Clear? The velocity variable. So this configuration variable consists of translation and rotation at the same time. So you can expect that we can define some variable that would correspond to angular velocity and at the same time linear velocity in one variable. This one variable, we call it a twist. We denote it by like this curly V. Okay, it's a capital one. And again, it's defined as the twist. Again, this is in tilde form, so you can expect this will be like a matrix. It has a matrix form of frame B with respect to frame S, and again, we can express it in any other frame. It lives at the tangent space to SE3 at the identity, which we call small SE3, which is the Lie algebra of the SE3 capital SE3 Lie group. And this is the kinematic relation between it. Familiar? Okay, easy. So now you know how to do rigid body translations, again, point mass translations, rigid body rotations, and rigid body motion in general. That's it. So again, so I think it took 5 minutes to go from SO3 to SE3 because everything is exactly the same. Abstractly, everything is the same. We just have a different manifold, a different Lie group, but everything we saw is exactly the same. And again, we have here also the special Lie algebra. Everything we want to do here, we just map to the algebra. It has a vector space structure, it's the identity. Everything is nice and easy. What we're going to be doing in the rest of the lecture today is play around with these matrices and see how they look like and try to hopefully show you that you already are familiar with some of the stuff in it and some of the stuff are completely new. This is why we introduce this twist as a variable on its own. Any questions before we go? Yes.
Because like for a curve, when you take the tangent, it takes
That's okay. That's a good point. If I let's look at the plane and I give you a circle in it, a point that's moving on the circle, what's the dimension of its velocity at any point? 1. It can only move like tangential, right? So it can move. So for example, if this is the circle, this is the point on it, it can move, for example, in this direction. If it comes to the point down there, it can move this direction. You see, it has 1 dimension. So it's a 1-dimensional manifold in a 2D space. You visualize it in 2D. And the velocity lives in 1 dimension, which is in this case R. Take the sphere. If you're on the top of the sphere, if you're at the North Pole, you can go right or front, right, left, or front, back. So you have 2 dimensions. And the sphere is also a 2-dimensional manifold that you visualize it in a 3-dimensional space. You always have that. For in general, the tangent space for any manifold of dimension n has the dimension of n also as well. Okay, so that's in general. Another question? Yeah.
The reference frame for the moving body or the manifold.
Very good point. There are no reference frames here. The reference frames you're thinking about live in R2, right, or R3, right? It's like in physical Euclidean space we're living in. And this is where we put the reference frames. This is something completely abstract, okay? And so what here was represented as a 4x4 matrix that you use to move stuff around is here just a point on this manifold. There's no intuition. That's why it's abstract. It's abstract. It's not that it's not related to the physical space we're living in. It's just that what is the space where the homogeneous matrix lives in? It lives on a manifold. This is, you can visualize it as the following. Oh, okay, let's go back maybe a little bit. We said the dimension of SO3 is 3. That's why you always think of rotation as in 3 dimensions. It makes sense, right? You rotate around X and you rotate around Y and rotate around Z. It makes sense. If we have here a 4x4 matrix, what's the dimension of it? Supposed to be 4, but there we had a 3x3 matrix. The only thing we added from going from SO3 to SE3 is R3, right? If you remember, at some point we said SE3 is just SO3 and R3 combined together, but was what was called the semi-direct product. So SE3 has a dimension 6 because it's rotation, 3 dimensions, and also translation in 3 dimensions. The Lie algebra of the Lie group has also dimension 6. But again, when we write it in this form, remember that we are representing everything as 4x4 matrices. So this is a 4x4 matrix, which is the homogeneous transformation. This is another 4x4 matrix. And this V tilde will be a 4x4 matrix in this matrix form. But this 4x4 matrix has 16 entries. A lot of them will be zeros. A lot of them will be related to each other. What's the actual dimension of it? It's 6. That's why we can represent this matrix form as a 6-dimensional vector, what we're going to be calling the twist. So 3 of these numbers will be angular velocity, 3 of these numbers will be linear velocity. So you see, so the twist is a 6-dimensional vector that corresponds to linear rotation, linear velocity and angular velocity in one vector. If we go back to the omega hat, it was a 3x3 matrix, and we can represent it as a 3-dimensional vector. Of course, all of this is what we're going to be writing down in details now. Okay, shall we start? Okay. This is what we're going to be doing, inshallah. Hopefully, in the remaining time, we're going to look at more details on this Lie algebra SE3 of the Lie group, capital SE3, and then we're going to be looking at some very useful properties of angular velocities and twists. And this is really the most important part because this is the tools that you're going to be using. Okay? If you want to throw everything related to the abstract thinking, throw it and focus on this part. You're going to live the rest of your life well, and you're going to graduate, inshallah. Okay, so let's move on. Where's there it is. So let's go to the whiteboard. Let's make it. Now let's look at what we call the H dot. Let's start with the H. If we have some H with respect to of I with respect, let's use the same values we had. So B with respect to S. Then this is some R, B with respect to S, 0, 1, psi of B with respect to S. Familiar to everyone? Now let's look at what the H dot is. Again, in terms of matrix multiplication, or again, in terms of matrices. So HB with respect to S is simply the RB S dot psi B S dot, and 0, what do we put here? 0. If you differentiate something that's constant, what do you get? You get a 0. Okay. So this is how the H dot looks like. Now let's multiply both, right? Because what we define to be the twist in the tilde form, we said that the twist of B with respect to S expressed in which frame do you want first? S frame. Okay, let's choose the S. Let's choose the B, so it's easier. Okay, so let's put it in the B frame. Then we're gonna have. Does anyone remember the indices? Okay, so I think last time someone asked about the indices. Okay. Is there an easy way to remember them? Yes, there is a very easy way. Let's write H and H. We're interested in having the B frame, right? We're expressed in the B frame. So this index should be B. If this should be BB, what should this be? If this should be S, this should be. If this should be B, that's it. Easy? Okay. Okay. If you have mistakes in this in the exam, it's not forgiven. Okay. Where should the dot be? The dot should be with the variable that we are looking at its relative velocity. So I'm looking at the relative velocity between frame B and frame S. So this is the velocity. So you can expect that this should be related to the variable that has the B down, the S up, which is this one. Easy? The same holds also for the angular velocity. So if I replace this by omega and this by r, everything remains the same. Clear? So let's look at this one. To do that, we need the inverse of HSB. So HSB is the inverse of HBS. How was this inverse defined? We said that this is RSB and this is minus RSB multiplied by the psi of, can anyone say what should this be? Should it be BS or SB? S down or B down? Why? No, I'm talking about the psi. I'm talking about the psi. Again, to never make mistakes. This is an S down, which means that it's going to map some vector in the S frame to the B frame. So where should the psi be represented? In the S frame. Again, you remember this idea of that these should cancel out, or at least these should match. So these frames should always match together. Okay? The same here. So if this is S down, this should be S up. You can never make mistakes in this. Even if you don't remember any of the formulas, you can always recover them at any point, even if you're on an island alone. And this should be the B. This is 0, and this is 1. The RSB is just another name for what? RBS transpose. Okay. Now let's plug again, matrix multiplication, nothing fancy. So I'm going to use this part here, RSB minus RSB BS 0, 1, multiplied by the dot. Clear? What's the result? Again, this is matrix. Okay, that's 3 by 3 will be multiplied by this 3 by 3 matrix. So we're going to get here another 3 by 3 matrix that looks like this. And then we have this part multiplied by 0, so we don't add anything. Then we do first row, second column. So we get, and the rest are zeros because we're going to just take 0 multiplied by 1 to the second row here, so it will be copied the same. So you see V tilde has this 4. It has zeros down, and it has here some 3 by 3 matrix. And this is a 3 by 1. Sorry, this is a 1 by 3. Yeah, 1 by 3. And this is 1 by 1. And this is what? What's the dimension of this? 3 by 1. So in the end, what's the dimension of this 4 by 4? Matrix multiplication, everything is easy. Now let's look at this guy. Did we introduce this guy before? What did we call it? Omega tilde. Now can you play the game of the indices and tell me the indices, what they will be? Which one is down? With respect to? Expressed in? And it makes sense, right? So this 3 by 3 component of this 4 by 4 matrix is nothing else than the angular velocity of frame B with respect to frame S expressed in frame B. So there's no magic there. What about this guy? So psi B with respect to S dot. What is this? What's the dimensions of? Oh, sorry, not the dimension. I mean units of it. If psi from B to S is in meters, what would this be? Meter per second. So we're talking about what? What kind of velocity? Linear velocity. But we're just representing it in what? In frame B. So this is, again, it's a quantity of how the origin of frame B seen from frame S is changing. And I'm just representing it in frame B by this transformation. So we're going to introduce this new variable, small v. This is different from the capital V. The capital V, we call it the twist. The small v is what we're going to be calling the linear velocity of frame B with respect to frame S expressed in frame B, and everything else is zeros. 1 by 3, 0, and a 1 by 1, 0. And this is simply what we call the matrix form of the twist. Okay. And now you see, now let's just do a small exercise. If we have rigid body motion, that the orientation is not changing. So I started from some orientation, and I'm just translating. What would be the RB with respect to S for all time? No, RB with respect to S, identity. So if this guy is the identity, then what is the relation between these two? They are the same. And this is exactly what you know in linear translation or point mass dynamics. So the kinematic relation between the rate of change of the configuration of position is the velocity, only holds if you don't have orientation change. If you're rotating and at the same time you're moving, you get this coupling between velocity, and the velocity is not the rate of change of position. Of course, if this is 0, this is 0. It makes sense, right? Because this rotation matrix is the linear map between R3 and R3. And this angular velocity written in a skew symmetric form is nothing else than just some fancy way to write three-dimensional vector, which is the omega you're all used to, rotation again around some x-axis and y-axis and z-axis, angular velocity, which says that this 4x4 matrix written in this way is actually isomorphic to, I can rewrite it as, now let's define this isomorphism, okay, this map that would take this 4x4 matrix and just put omega b bs on the top and v b s on the bottom. And what's the dimension of this? It's in 6, because the first one is 3-dimension, the second one is 3-dimension. But this is a 4x4 matrix. In other words, this lives in SE3, small SE3, because this is an element of the algebra. Oh, and this is its corresponding, like some isomorphism. We're going to be calling this isomorphism S tilde inverse. This is just a name for it. If you go from this guy to this guy, we call it S tilde. You go from that guy to that guy, we call it S tilde inverse. It's just a name for taking all of these elements and putting them in a vector form. Easy? That's it. So again, we could have started from here, but you can now appreciate everything is matrix multiplication, but you either know these tricks or understand the math that's behind them. Okay, you prefer. Okay, if you prefer to forget the math behind them, move from the tricks from now on. Any question before we move on? Easy? Okay. Now let's look at the other one, which is VB with respect to S expressed in S. That I leave for you as a homework. Okay, it's very easy and it's trivial to do. Okay, it's just you're going to multiply this one by that one. Will you get the same expression? No, of course not. Okay, we're going to get something else. This something else, even though it will have different relations, so this V tilde of B with respect to S expressed in S will have omega tilde B of S with respect to S, 0, 0, and VB SS. So again, we're going to have some angular velocity expressed in the stationary frame and some linear velocity expressed in the stationary frame. Now a question to you. Think about it for a second. The linear velocity expressed in the stationary frame, isn't it just this guy? Think about it for a second. Intuitively, who says yes? Intuitively. Okay. The rate of change of some point that's moving, when I look at it from the S frame, is the same as taking the position of this point moving around and looking at it from the S frame and differentiating in time, right? The rate of change of position is velocity, right? Rate of change of position in the S frame and velocity in the S frame. They should match, right? Look at now the expression for this, and you're going to be surprised of how this is completely not equal to that guy.
Assuming if the frames are moving relatively together, then
Just follow the math. Follow the math blindly, and if you find that this guy, which is the linear velocity of frame B with respect to frame S, as seen from frame S, expressed in frame S, is equal to the rate of change of the origin of frame B with respect to S, just divided by time, right? Let me know. Question.
What about the rotation matrix? What is the SP for the rate we change for sort?
This one. What about it? Yeah. So you're asking what is this operation, right?
From this direction to another direction.
Yeah. Okay. So you're thinking of this as a vector, and this is rotating it, right? That's not true. What this is a vector of the point B as seen from S. So in other words, expanded in the bases that you chose at the stationary frame. And this is just a way to rewrite, it's a linear map that would take you from this basis as seen in the S frame to the bases as seen from the B frame. So this is just a map that would change bases. Okay. So this is what the rotation is. Small b, okay? B with respect to S expressed in B, yeah. It's always the linear velocity. It's always the linear velocity. This is what we call the velocity. This is what we call the rate of change of position. But, okay, what I show you from here is that the rate of change of position is not the velocity in general. Okay, they only coincide if you have no rotation, which was the case when you had a point mass. This means that the rigid body moving from this point to that point is not rotating. So it is as if it's acting as a point mass, right? If you have a rigid body that's not rotating, then it's as if it's a point mass. So this is what this says. Okay? Then when you take the rate of change of S with respect to B for all time, you're going to find it's zero. It doesn't have any angular velocity, but it has some linear velocity. So you just go back to the case of a point mass. Okay? And the same also here. If we have a rigid body motion and rotation, in general, and you're not translating, you're just rotating at the same point, then this guy would be zero. This guy would be zero, and you just recover here what the angular velocity is. And this is why this is the general way of doing it. Just if you're writing a code, you don't think of am I doing translation and am I doing rotation separately? No, there's just one thing given by this. And if you're at some point you're translating and not rotating, it's captured. If you're at some point rotating and not translating, it's also captured. And the math works. Any questions? Okay, let's move on. Now, this is the matrix form of the twist, and this is its 6-dimensional vector form of the twist. So 6-dimensional, and this should also be 6-dimensional. It's just some 4x4 matrix written in this form. Now, there's a question that, definitely will come to your mind. These two should be related to each other. If I have angular velocity represented in frame S, of B with respect to S, and I look at it in frame S or in frame B, there should, of course, be some relation, right? What do you think looking only on angular velocities? If you look at angular velocities only, so we said that, so angular velocities, so omega tilde B with respect to S expressed in B, and omega tilde, let's not the tilde. Omega, this is not. Okay. Omega B S S. Just out of the top of your hand. of your head. What do you think this transformation will be? That to represent this vector represented in the S frame, looking at it from the B frame, what do you think the transformation will be? The rotation matrix, S to B, right? So these two always have to match together, okay, because they cancel out. So this is the variable, okay, this is the frame where we're representing this vector. What is the name of the vector abstractly? What is the name of this vector abstractly? It's the angular velocity of B with respect to S. It's defined no matter what frame you look at it from. So my velocity with respect to you is independent of who looks at this velocity while I'm moving, okay? Because if you're moving and I'm moving at the same time, then my velocity with respect to you would be some sort of like some difference between our velocities, something like that. Okay, so this is what this expression says. Can we prove it from what we have? Okay, so what we show that omega, the proof of this expression, even though it makes sense, but the proof of it can be found from this expression, that RB with respect to S dot is at one hand omega tilde B BS of RBS, and at the same time it's also what? BS. Everyone agrees? So you see that these two are related because they represent the same tangent vector at the tangent space to the curve that represents this rotation of a rigid body. So these two have to be the same, which implies that this guy in tilde form is equal to R SB omega tilde BS S R BS. Okay. And you see what will happen here is that we have that these three indices, they're like connected to each other, right? Okay. So they have to be the same. Now, can we show that this guy, so this is written in a 3 by 3 matrix form, right? It's a skew-symmetric matrix, and this is a skew-symmetric matrix form. Can we show that this is equal to, would lead that when we remove the tilde form by going back and like to the three vectors, that this is equal to that expression? Yes, you can show that, okay? Part of the assignment. The proof of it is also in the book, okay? So you're going to be starting in the assignment, try to think about it yourself. When you face some part that's too difficult, go to the book, get some hint and go back, try to do it yourself. But it's very easy to prove, okay? And this is some sort of, again, you can think of it as an identity, that if this is the relation between the angular velocity in vector form, this would be the corresponding relation in skew-symmetric form. So in other words, this is how these two elements of R3 are related, and this is how these two elements in SO3 are related. Okay. In the end, of course, there are two vectors that are related by some sort of expression, right? We're just taking that vector and representing them two together. But you see, when you look at it in R3, it makes sense. You just have a linear map from R3 to R3. But again, this SO3 is again a vector space. It's just nasty looking vector space. You cannot visualize it. And we still have some expression that would take this vector to that vector, this expression. Clear? So this is part of the homework you're going to be working. This is interesting because what is now the relation between the twist as a vector form in 6 dimensions to the twist, okay, in S frame, and the twist as a vector in the B frame? And this is this expression we're going to be deriving now. We're going to be using it for the remaining course. Okay, so pay attention to this part. So this is part of the homework. The next we're going to be doing together. Okay, so but this is something you can do at home. Now let's look at the relation between twists. Yes, Farouk.
Previous slide. Previous slide. Previous slide.
Previous slide, which is this one. Yeah.
The right side. This equation. This one on the right. No. I mean.
This one?
No, the second one.
Second one?
Yeah, the right side. Shouldn't it be SB?
No. BS, BSS. Take this guy, transpose it, put it here. You're going to find that the same formula we said.
Right.
because very good point. So Farouk is saying that we had that in this case that this B and this B they match together. Okay, because this is where this vector is represented, expressed, and this is the map that takes you from this frame to that frame. But this vector, where is it represented? In the S frame. Okay. So now you're going to be saying, okay, what is the map that takes this vector to, but again, you see we're not multiplying it here by anything. This is how you're going to be transforming something like that. And again, if you look at it only, and this is one of the ways that one of the places where you want really to understand what's going on in the abstract way of thinking, because even if you try to put some rules like this, we're playing around with matrices, at some point they won't make sense. But if you understand it, this is a tangent vector, and I transform it to the algebra by this approach from the left, then this is the right way of, right as in right and left, okay? So right, okay, translation of this vector, okay? Okay, so this is called the left translation of the vector to the algebra, and this is called the right translation of the vector to the algebra. Right? Left translation, right translation. Yeah, start. Yeah.
Quantity belongs to this omega tilde B is
Which expression here?
no, the
Here. Yeah.
Transforming this one. I don't thinking of this is true.
Yep.
But we will transform this one from omega tilde from B. No, that one, the second equation.
This one?
Yes. And we are taking with the stationary frame S, right?
Yeah.
The quantity will change definitely there, right?
I'm sorry, I don't get the question.
The elements of that, like that's the 6 degree of freedom, right? Now omega tilde B.
Omega tilde is a 3 by 3 matrix that's Q-symmetric. So it has 3 numbers in the end. That are
those elements
yes
change from whatever we have
here.
Yeah.
So this expression you mean? So this 3 by 3 matrix is different from this 3 by 3 matrix. Absolutely, because they both represent the same thing from 2 different frames. So they both represent the rotation of frame B with respect to frame S. Okay, you see, this is common. So this part is common. BS, because they represent the same thing. But what's inside here is just how you see which frame you're looking at this angular velocity from. So here I'm looking at this angular velocity from the body that's at least from the frame that I'm rotating with. So here the observer is rotating with the frame, but here the observer is fixed. Okay.
If we take the R matrices for both to the left hand side, to the part of R dot, then it is preserved. Take the RS.
This one?
In front of the original, the first value.
Yep.
If I put it in front of it, it is preserved. It is BS.
SB.
Yeah, if it is the first one, it is SB.
SB.
Yeah.
And if I do it here,
then
it's SB.
It's BS.
No, SB.
Yeah, SB, yeah, down up. Yeah.
Yep.
SB.
So
it is
BB.
preserved here,
Yeah.
but here is not preserved.
No, it's the same. So again, go back to the expression. Maybe let's go back to the slides. Yeah, okay. Okay, here.
So, yeah, here it is preserved.
Yep.
No, here it's not. It's not.
It's the same expressions. Everything is exactly the same. Take your time to look at it in detail. Okay. So these are exactly the same expression.
Here it's not preserved.
When you multiply from the right here by RSB, this cancel out, and the RSB comes down up from this side.
Yeah, that's what I said. That on that side it's preserved. Yani SBBS.
It's here it becomes SBBS.
Yeah.
So the frame B they cancel out from the right, but from this side when you multiply here RSB, then the S frame will cancel out.
That's what I was saying. They cancel out on the left.
The S cancel. Yes, exactly.
On the right side they don't cancel out as in the second case.
another two indices cancel out, not the same indices. So let's see if we have here. So these two indices should cancel out. But if you inverse the relation, these, okay, if you put it from the right side, then it's maybe this one and the other one. Take a look at it and write it down, and then we can look at it indeed, okay, after the lecture. So yeah. I don't memorize it. I just look at the indices and it works out. Don't memorize it. Just look at it in the indices. You can always recover it this way. Good. Where was it? Yeah, here. So again, RBSB. Okay, so BS, these two cancel out. Then I get the B. I put the B here. That's it. If you want to say, okay, it's always multiplied from the left, you go to the body thing. Okay, you multiply by the right, you go to the spatial. That's okay. Okay, no problem. But what if you have a third frame? Then it becomes nasty. So don't memorize it. Always go with the indices. Okay.
Okay, so that those are saying that it is preserved when it is R and R dots. We can always recover this back easily from cancelling out the diagonal sides. But when I take the RB to the other side of this omega tilde, then the cancelling is not preserved diagonally.
Exactly. Yeah, that's right. As in the indices. But if you look at the R dot from the other side, it works. Yeah, exactly. This is just a notation. Okay, it's just a notation drawback. Okay, but the math behind it is the same. So just left translation from to the algebra, right translation from the algebra. Okay. Okay. Now let's look at the change of coordinates for twists. We said that HBS dot is equal to HB S V tilde B B S. Okay, works. And at the same time, it's V S B S H B S. Clear? Which implies that this guy is equal to H S B V B S. So this is how both of these are in SE3. So this is if I have some twist in some V frame or in some X frame and I want to go to some Y frame, this is the formula I have. Clear? Now let's make it interesting. What is the corresponding equation such that when I have the V in the vector form, which is in a six-dimensional form, VBBS, what is here the transformation? What's the map that will take me from this six-dimensional vector? Okay, first of all, what do you think the dimension here would be? 6 by 6, makes sense, right? So it's going to be a 6 by 6 matrix. We're going to be calling this matrix, this is the name of the matrix, then we're going to derive what it looks like. This matrix we're going to be calling AD, capital A, small d, and it's not some constant matrix. What do you think this matrix will be a function of? Look at the map there. It's this map going from this space, from this SE3 to this SE3 element. What was this map a function of? What information do you need to provide to it? The homogeneous matrix. I need to provide to it the homogeneous matrix. BS and SB. Is that correct? Do I need to provide two homogeneous matrices? Why only one? Because the same information, right? So what's in B with respect to S is the same as what's S with respect to B, just represented differently. So this is a function of the homogeneous transformation that would take you from B with respect to S. We're going to write it from S with respect to B. Why we chose to do it like that? Simply because to preserve, again, this indices, that if this is represented in S, then I transform it from the S frame and I go to the B frame, which is here. And again, everything else, which are these two, is just the name of the twist. This is very important. Because later on, when we have a third frame, so let's say I have the twist of B with respect to S in frame Y, and I want to represent the twist of B with respect to S in frame X, then what do I multiply here? H of Y with respect to X. That's it. So that's why the B and the S here are just because we derived them this way, but you can have a third index. You can always look at twists and angular velocities and velocities from a third frame. And again, this is what I mentioned last time explicitly. Velocities always have 3 indices. So a velocity always has 3 indices. Now let's look at this expression. What does this expression look like? And what we're going to be doing is just expanding this matrix, trying to figure out what kind of, what the 6 vector that's in here, how is it related to the 6 vector in here? So it's just some matrix manipulation, nothing fancy. And let's do the proof as follows. So let's take this expression and write it as like this. So let's do it here. So omega tilde BBS 0, 0, VB, BS. This is the matrix form of this twist. All agree? This is H, sorry. This is here, the rotation matrix SB, the psi SB, 0, 1. And again, the psi SB here, I can rewrite it as minus RSB multiplied by psi BS. Okay? So this is the expression. I just write it like this for simplicity, and we're going to expand it later. Then we have, in this part, we have VBSS, VBSS, 0, 0. And on this side, we have RBS, psi BS, 0, 1. Clear for everyone? Easy? Okay. Now let's, you choose. You want to multiply this one by that one or this one by that one first? First one, okay, let's multiply this by that. The second 2 rows, you get 0. Because what this does simply is just it extracts the second row. Not the second row, the last row. Remember, this is a 4 by 4 matrix. So we're talking about here as the last row. Then we have that RSB omega BS S. And then we have RSB VB SS. Is that correct? Yeah. And this is multiplied by RBS. Now, we get this part multiplied by that part, RSB omega tilde BSS RBS. Then we have this guy multiplied by here. So this is RSB omega tilde BSS psi BS 0. 0, we should get a 0, 0, yeah. Clear? Easy? So far, so good? Sorry? Do you have a question? I'm just asking, is that clear up to here? Okay, so let's move on. How can we continue? Let's see. I'll try to squeeze it in here so that you have it all on one board. Let's look at these two first. Is there a mistake? Which one? So this one multiplied by this. Yeah, you're right. There's something wrong. Yeah. So this one is multiplied by that, and then we have this guy multiplied by, yeah, absolutely, you're right. So this should be an extra term here. That is RSB VBSS. Absolutely, yeah. Thank you. BSS. That's right. Thank you. So now, let's maybe take this matrix can someone take a note of it because I'm gonna write it down clean. Okay, take a note of it and then just please help out. So what was this matrix? So RSB omega SBS tilde RBS. This was this term, and then we have here RSB omega tilde VSS. Then we had V psi VS plus RSB VB SS, right? Okay, 0, 0. This expression, we're going to be writing it in this following manner. Let's take all of this, remember, was equal to omega BSB tilde and VB B, okay? So this term is equal to that term, and this term is equal to that term. Now let's try to write it down a little bit to massage this equation. So you remember when we said that this expression equal to that expression, what does this imply? It implies that omega B with respect to S seen from the B frame is equal to RBS omega SBS. You all agree? Okay. And then we have another expression which says that the VB, which is that guy, is equal to this sum. The first one, we're going to use a very nice property you're all familiar with, but it's just it looks different. When we have the tilde form of some vector multiplied by another vector, what did we call that term? So if we have omega tilde multiplied by another vector that's in 3 dimensions, what was this equal to? The cross product of, sorry, so omega BSS cross, this is how we're going to represent the cross, because I don't want to use the times because we used it for several places in the Cartesian product and so on, so just to make it easy. So this is BS. Everyone agrees? There's a famous property of the cross product. If I reverse the order here, what do I get? A negative, right? So this is equal to the minus of this vector product. Everyone agrees? But this is now the vector product of this guy, which I can write it as everyone agrees? With the minus. So this cross product, this is a vector. I can write it as a skew symmetric form. What am I doing now? Am I transforming some sort of tangent vector to the algebra? No. It doesn't work out here. So you see, the algebra has velocities living in it. This is not a velocity. This is just another way of writing this expression. You see? So now again, matrix multiplication, okay, it's very similar to before, but has a completely different meaning. So this now expression, let's plug it in there. So I have, this is RSB multiplied by, there's a minus here, and there's psi BS. Let's multiplied by omega BSS. And then I have another term, which is RSB VBSS. What I'm going to do is just write these two equations into one matrix form. The matrix form looks like this. Clear? Looks nice. So this is a 6 by 6 matrix. It's a function of RSB and psi BS tilde and RSB again. So it's a function. So this is what we wanted to call. So everything in here, this part, so I can rewrite it as add H SB multiplied by the vector omega B SS VB SS. But there's just one small technical issue, is that this is the rotation matrix that we got from this homogeneous transformation, SB. While this one, this is not the same, right? Can we write it in terms of SB? Yeah. Transpose? No, that's not the case. Now let's expand this part. Let's see. I'm gonna remove, I'm gonna just erase the first part. Does anyone need it? This top part, okay. So this guy here, which is just looks annoying, which is the psi BS tilde, is nothing else than the tilde form of the psi b with respect to s, which was actually equal to minus r SB BS, or in other words, SB transpose. Is that correct? Yeah. So this is minus R SB transpose SB. There is a very nice property, and it's exactly the same property that you're going to be using in the homework to prove this part. So this is like a proposition at like separately, that this guy here, so this is the tilde form of omega B S S of R SB. Does everyone agree that these two are the same? Everyone agrees that this guy is the same as this guy? What I just did is that I removed the vector part and I put this expression here, and then I take the tilde, and you see it's equivalent to that part. So this is already an identity that we can use, and we're going to be using it here. So if I have R multiplied by some vector, and I take the tilde form, or this, I make this into a skew-symmetric matrix, then you can write it as this expression. Now let's write it down. I hope I remember the order. So SB, okay, so so SB, then the first one should be SB. So let's try to make this work. Okay, let's make this easy. So let's write this as, how much time we have? Okay, I have 2 minutes. Let's see. Now, BS. There's no dot here, so that's what we have here. Then we can use this expression. So we have a minus here, then we have a minus of RBS, this guy, tilde, RSB, okay? So this is the expression that we have. Let's multiply both sides by RSB. So if I multiply this guy by RSB, okay, so this will imply that RSB of this guy is equal to minus SB of that guy. Does it work? Yep, it has to work. So I just multiplied both sides. I took this part, send it there. So I have this multiplied by that. So the inverse of this multiplied by that is equal to the minus of this multiplied by that. Now let's take a look. You see this guy? I can rewrite it as this expression. So this is exactly what we're going to be doing. I'm going to be taking this remove this guy, remove the minus, and just write it as everything here is from SB. We're happy. So, and this is the corresponding matrix. So this is known as the adjoint matrix or the adjoint representation of the Lie group SE3. Okay? So this matrix is called the adjoint. Again, we derived it here in with some matrix manipulation that maps some 6 vector to some 6 vector. It's something very deep and it's related to the Lie group structure of SE3. Okay? This is why it has this fancy name. And this is where the AD comes from. So this is known as the adjoint representation of the Lie group SE3. You give me an element or a point on SE3, I can give you a map that will take elements from the Lie algebra to the Lie algebra. Okay, so this is an element in the Lie algebra which represents the twist expressed in some S frame, and I map it from the S frame to the B frame by this map that goes from the S to the B, and that's it. Any questions? Let's stop here for people who want to leave, and I can take questions offline. Okay. Next time we'll continue from here. Okay. So we're gonna have some nice assignment. No homework this time. This time it will be a graded assignment on this part. Okay. Thank you very much.